appropriately, the title of the talk was "Living la vida nube," living in the cloud, because that's what I'm having to do these days with a dead computer. So very briefly, by way of introduction, my name is Fernando. I'm faculty at UC Berkeley. I'm officially in the statistics department, but I was trained as a physicist. Actually at CU Boulder, where Julie is. I did my PhD in the physics department there a long time ago in particle theory. But I ended up really building my career around the development of open source tools for scientific computing. Did a postdoc in applied math also at CU doing numerics, and operated a lot in the kind of NumPy, SciPy, Matplotlib, scientific Python space for a long time from the start. I started the IPython project back in 2001 when I was in grad school, which is what kind of became Project Jupyter with a much bigger community later on. And so kind of those first two decades of my career were what I would call the rise of open source science, right? This was an example of a talk that I would have typically given in LaTeX back in around, say, 2007, 2004, where there was a big, long blurb justifying what is Python, why should you use it, what is it good for science, etc., so on and so forth, explaining to people. And this was actually taken from slides from multiple conferences where I had things of that nature. The creator of Matplotlib, John Hunter, who was a good friend, passed away in 2012. And in a little eulogy that I wrote for John, we were very close, we worked together. I actually wrote this blurb that I looked at for the Jack Eddy event. I went back and looked at it because I remember having said something to that effect. And at the bottom of that eulogy, I said, historians of science will describe the period we're in right now as one of deep and significant transformations to the very structure of science. And I know that sentence sounded kind of grandiose, if you will, but I don't think it was wrong. I don't think it was incorrect, because I really do think that science was fundamentally transformed by a transition to open source, both tools and practices. And I think we've seen that in practice, right? I'm sure many of you are familiar with this figure. This was the figure one in the very first big paper that the LIGO collaboration published from the binary, the first detection of gravitational waves back in September 2015. That figure is entirely made, right, with the scientific open source stack. It's NumPy, SciPy, Matplotlib, the various color map in there. This is a figure from a paper that will probably be one of the most cited papers in physics for the decades to come. That led to a Nobel Prize 2 years later, and all of that entire work was done with the scientific open source stack. So in fact, science had become standard to do science in this way. The LIGO Open Science Center published Jupyter notebooks that were runnable on Binder, giving anyone with a web browser basically the ability to rerun those analyses, look at those data, listen to the sonification of the data, etc. So same thing a couple of years later when Katie Bauman was presenting at EPFL her work on the imaging of the first direct imaging of a black hole from the EHT collaboration. She did an analysis together with GitHub of the streams that feed into their codes, into the codes of the EHT collaboration, and they found that if they kind of deconstruct the dependency graph for all of that, and they do a head count on GitHub, they found around the order of 23,000 people had given them effectively the tool stack, not to do it in IDL, which would have been kind of the expectation maybe 10 years prior or 15 years prior. I started IPython basically to move away from IDL back at CU, and instead it was this giant community of contributors that gave them those tools. Now, I would argue this has been successful, but that now that's not the game anymore. The game of doing science with open source tools is kind of a given at this point, but something new is changing. And I would argue that Kjell Ganteman, who is simultaneously leading the change to open science at NASA and in other spaces, has also been one of the people who argued best for this other transformation, which is kind of the arrival
this meeting is being recorded.
Of cloud-based tools as a de facto platform for everyday science and education in modern research. Kjell and a couple of other colleagues, including Jim, who couldn't join us today, and some of the folks from our team at Berkeley, wrote this paper that I highly recommend, which is kind of a high-level overview of this vision of doing science in cloud, and it's illustrated with a couple of cool tweets. Kjell is an oceanographer by training, and she works on sea surface temperatures. And here she is doing kind of large scale science through a cloud hub on a $30 Raspberry Pi at home with her kids, right? And Julius Busicki, who's also an oceanographer, was tweeting something similar, doing pretty large scale data analysis via his phone on the New York subway. Shell is now leading the TOPS initiative. This is probably not news to anyone in this community, given that you work with Ryan and Julie and others who are involved and invested in these kinds of efforts. This is pretty transformative. I mean, going to DC and seeing program officers from NASA kind of recite federal policy, SPD 41, that indicates how everything that NASA does from now on and everything that NOAA does when NOAA officers stand up has to be done in the open from the get-go, right? We're not just talking about, well, if you email me my postdoc, if they're back from their backpacking trip in Indonesia, I will send you a zip file with some stuff that you can read. No, it is, if you're doing science funded by us, the design is open, the workflow is done in the open, codes are maintained in open GitHub repositories with community input, so on and so on and so forth, with a very thoughtful process about culture, practices, training, education, access to code, etc. That is truly, truly a transformation in science, and seeing this happening pretty much across every federal agency is I think, a sea change that I'm delighted to see. Now, moving towards the cloud, what I think we have is an opportunity of combining a few kind of related efforts and initiatives, right? We have on the one hand data that is openly accessible, that obeys our principles, and there's a lot more to be done in this regard. I'm not pretending that we're all done here. There's in fact a lot of discussion around the data issues that is fascinating, and that folks from that same paper are working very actively on, like Ryan Abernathy. But we do have data that can be combined with computation that is scalable and that can be brought next to the data, right? We have the flexibility of computational resources, and we have the ability to bring those resources next to the data in ways where the opposite is not possible, right? We can't bring CMIP6 to the computer. We can't download 20 petabytes of data anywhere, but we can bring a few hundred megabytes or a couple gigabytes virtual image into the cloud and park it next to where the data is, instantiate it in whichever specific hardware constraints we want, and use it once we embody that resource with tools that we are free to assemble, right? We have tools that are modular that we can compose and recompose in the way that we need. And those three factors put together really open up what I call kind of the metaphor that I use of the watering hole is that there's this place that has a resource, the water in the case of the real watering hole, right? Where the lions and the zebras come together, right? Different species, different actors who have different needs, who may even be competitors in some cases, have a need and a reason to come together for this common resource and can act together in new and interesting ways. And this gives us tools to go across disciplinary silos to work on problems that go beyond what one person, what one small team can do, what a traditional discipline does, to combine data sets from multiple sources and to ask questions that scientifically are, I think, the most relevant ones in challenges like climate change, like solar system physics questions of the kinds that I remember Ryan describing the solar physics community tackles, right? And problems that involve everything from low-level, very, very technical domain-specific questions all the way out to societal impact, right? Because in the cloud, we can involve others. We can involve other stakeholders.
Now, I want to
Yes, please. Oh, yes. If somebody's asking, I'm on the iPad. I only see Julie. So please just yell and go ahead.
Gotcha. On the previous slide there, I was just going to ask, yes. What was that picture in the lower left corner? Was that a watering hole, or was that something else?
Yeah, no, that is a watering hole.
Oh, cool. Yeah, I don't know if you're able to like scoot the Zoom participant window off to the side so that it collapses, but we see ourselves on the screen sharing too.
Oh,
so
you do? Oh, I'm
slides.
sorry. Okay. Let me. Yes, got it. I do get it that you're recording. Okay, I wonder how.
Yeah, if you just slide that all the way to the side.
Oh, there you go.
Yeah, there you go.
It went to the side. Oh, okay, there you go.
And beautiful. That's a bunch
sorry
of
about that.
zebras around a whole bunch of water. Yep, nice.
Mhm.
Good metaphor.
No worries, Fernando.
I'm sorry that had been having your own faces on the video all the time. I wasn't sure how screen sharing on the iPad worked. Sorry about that.
No worries.
No,
So to this vision, we have to contend with a couple of important challenges that at least I want to put on people's mental radar. One is of what I would call competing visions of computing. Today in the world, a lot of the computing that we use, including this device that I'm using right now, an iPad or a phone, is predicated on a computing model. I don't care about the OS specifics or the brand or anything, but I want you to think about the computing model. The computing model of mobile devices is one where you as a user have access to apps. Apps own data, and they may share data with one another if there's a specific channel between two specific apps for sharing data. And those connections go through a bus that is mediated by the operating system. And on both Android and iOS, there's a specific little icon to do that, like, oh, do you want to share this thing with that app? And if anybody has tried to do like complicated multi-file, multi-format operations only on an iPad or a phone, you'll know that this can be a nightmare if the connection between two things that you need to do doesn't exist, right? And then you're helping like, well, can I put this on Google Drive and then maybe pass it to Dropbox and then maybe the other app will be able to see it, because the control of the architecture is in the hands of the vendor. Now, classic computers, by which I'm talking a Unix machine, a Windows computer, a Mac OS, any desktop classic OS had a different model. You as a user had access to data. You had a file system and you had applications, and those applications would operate on those data. And that's the end of it. Now, they might own some little bits of private data, configuration data, some indices, whatever, but for the most part, their access was to all of your data, and you were free to mix and match those applications you see fit, and you as a user have control. And I would argue that this is the model that we need to protect in a world that is trying to kind of appify computing, because the role of science is to create new things and to discover with new tools which questions we're asking of nature, not simply to perform specific tasks that are constrained by an app. And so as we think of computing for science in these new modes, I think this is perhaps kind of a bit of a sideshow, but I actually think it's a really important architectural distinction to keep in mind. And the second one is that in the cloud, nobody can hear you scream that it's free. It's free as in speech, meaning licenses are not enough. It's perfectly possible to be fully open in the cloud in terms of open source code, and in practice to be fully proprietary. And this is not an attack on Google or Microsoft or on Amazon. This is an issue that is kind of intrinsic to the modern web. These are vendors that are businesses that have an interest in providing proprietary services that are optimized for their platform, that attract people to pay for their services. That's perfectly legitimate business behavior. There's nothing wrong with that at all. But as I said, our mission is science and education, and we are not in the business of building Google science or Microsoft science or AWS science. We're in the business of building science, and it's very easy in the cloud to, even if you do everything with open source tools, to inadvertently end up deploying something that only runs on one of these vendors. You can think of these as effectively 3 proprietary operating systems with proprietary APIs. And if you're not very, very thoughtful, it's easy to fall into the trap of having something that can't be moved around or translated. And so for discovery and learning, we require creative freedom. We require the ability to mix and match our own tools. And I think we can do this. And I think I want to show briefly a very tentative proof of existence, if you will. This is drawn partly from research work and partly from my teaching at Berkeley last spring, a course called Stat 159, Collaborative and Reproducible Data Science that I taught. I don't have time to give all the details of the course. I'd be happy to talk about that to some of you if you're interested later. It's a course that's very much inspired by this classic quote from David Donahoe, John Buckheit. We're paraphrasing a geophysicist, John Claerbout from Stanford, and who said that effectively real research, the real scholarship is not the PDF. It's the entire stack of code, of data, the software environment, and these days probably where to run the code, because even if I give you all the code, it may be tricky to get it to run, to generate that scholarship and to generate the paper that we normally think of as the scholarship. But that is the true scholarship. It's not the PDF. The PDF is the advertisement, if you will. if you will. And this course is a course where I take undergrads across, it's taught in stats, but it really undergrads from many, many different departments attend, and we try to teach them concepts and skills to really use the computer as a creative thinking tool in modern open science research. And so it's really structured around a set of ideas that are on the left. The specific tool that we use is listed on the right. The tool matters less. You could replace Python with R or Julia. You could replace any of these tools with something else, and it wouldn't matter all that much. I think it is important to keep these ideas as the ideas that structure the modern scientific workflow. For example, that everything is done with version control from the get-go, that computational hygiene should be a daily habit. It's much better to brush your teeth than to get a root canal. It's a lot less fun. So reproducibility at the time of publication is too late, right? Instead, if you have a good daily habit, then by the time your paper is accepted, if you've made it reproducible from the get-go, it won't be a problem. And the way we enforce that is simply by having the class itself run on Git. So we teach them Git at the very beginning, and then we take them through a semester's worth of doing homeworks, of doing assignments, of doing everything through Git so that it does become second nature. We use GitHub Classroom, which is a tool, a cloud-based tool that lets us manage assignments and groups and student groups and whatnot for doing homeworks through GitHub. In there, they learn to create repositories that have a proper makefile to run the builds, that have an environment file that specifies dependencies. They learn then how to live the rest of their life reproducibly with Git, how to manage the configuration of their computing environment with Git, how to manage the skeleton of their home directory when they come to a new computer in the cloud or their laptop with Git. And so they begin to pick up habits that make it easy for them to move from system to system and to do it reproducible. At the end, reproducibility is all about effectively being obsessively machine-oriented, so that when you're in a new environment, things can be recreated automatically, because ultimately we want machines to be able to recreate and re-execute a lot of what we do.
On that note,
yes.
I have a comment.
Yes, please.
Are you familiar with the concept of reproducible papers at all?
Yes.
Yeah,
I mean, in general, yes. I heard you mention something along those lines earlier, and I'm obviously very interested. A lot of what we do is in this space.
Yeah, I mean, basically, I just published a paper where the gist of it was we wrote the entire paper both as the Word doc form Frontiers wanted and in a Jupyter notebook, where every time we had like a plot or a table or anything, the code that generated that was right there in line with the text. So it's like you're reading a paper and then suddenly, boom, you can execute the code that was part of the research. And I think that totally blends in with what you're talking about here with being
absolutely
oriented.
Wonderful. No, I'd love to see that work. That is very much the philosophy of the course, and we'll get to a flavor, I think, what you're just describing in a minute. Awesome. So the students learn about managing their dependencies explicitly. What does it mean to know which libraries your code needs and how to manage versions and so on and so forth. They learn then how to make their work available, right? So Jupyter Book is a tool that goes very much to what you were just saying. I'm sorry, I missed your name, and I'm not saying
that was Sean talking.
Sean. So to kind of in the spirit of what Sean was discussing, the students learn how to use Jupyter Book. Jupyter Book is a tool that helps you turn a collection of notebooks, markdown files, and restructured text files easily into a live website or a PDF, if you prefer. And so they learn how to use this as part of their workflow. They then learn how to make it available for others to execute via Binder. For those of you who are not familiar with Binder, Binder is a tool that allows you to take a repo on GitHub. And this is back to the toothbrush metaphor, a GitHub that follows good practices. If you have a repo that has in it an environment file with the right dependencies, you basically don't need to do anything else. It is reproducible by default. Binder will recognize it and make a live version of that repo automatically for you that you can give a link to others to execute. And it takes care of all of the cloud magic and Docker and Kubernetes and so on and so forth. So the students learn how to do this, and they see it in their everyday practice. For example, the course itself runs as a Jupyter Book published website for which there is an environment file. And every time the instructors make a commit, GitHub Actions automatically takes that commit and turns it into the live website. So the students see us do commits 5 minutes before class, and by the time we walk into lecture and connect the laptop to the projector, those commits have been rendered and have gone live, and the students learn how that works. And then Thank you, Sean. And at the end of the project, at the end of the class, they turn in a final project, which is very much kind of in the spirit of what Sean was just describing. They have to include data. They have to include code, which has to have tests. They learn about unit testing and so on and so forth. They have to have the notebooks that produce exactly what Sean was saying, right? If there's a table, if there's a figure, if there's anything that is going to be included in the main paper, then there has to be code supporting it that is available within the same repo. But the main narrative itself is a separate document, because the main narrative may be in a different order than the specifics of the analysis and getting the code to work and so on and so forth. And they include all that together with reproducibility support and good repository practices like licensing and so on and so forth. So they sort of learn how to follow kind of a standard playbook for modern reproducibility. This is an example. I should have updated the slides. I have some slides from this semester, but in a different talk, but they didn't make it to the one that I was loading into the iPad. Sorry about that. But this is an example just from a previous semester of how that works. They give us repos that run on Binder, that have a detailed explanation of how to run the code. There's analysis, there's code. The main narrative is something that reads like any scientific paper, right? That they can turn into, we can turn into a PDF, and in fact, they have to do that. And all of this, they do it in this cloud-hosted environment where they see a unified experience. And that's part of the point of doing it with these tools, right? Back to the kind of the conversation from the beginning, is that this tool, which for them is something that they sign in with their UC Berkeley credentials, is a hosted installation that gives them a full compute environment. It's not just notebooks. We run on something called Jupyter Lab, which is the current version of the UI for Jupyter. And in Jupyter Lab, you have access to data, you have access to terminals, compilers, you have access to normal files, editing Markdown files, LaTeX files, Python scripts, C files, etc. They can render those files. They can install that exact same environment on their personal machines, and they learn how to do that. The course is run in the cloud, but halfway through the semester, we teach them how to do it locally. And this environment, Jupyter Lab, as I mentioned, is one that offers kind of all of the tools, kind of a modern scientific workflow. The reason we built Jupyter Lab this way was because we needed something where we could edit Markdown files, we could preview a Markdown file live, we could have access to a terminal to do regular command line work, right? Running a compile job, running a big build, debugging something low level. We can access data files, and we can view a CSV right there. We can view images. There's some apps that are actually available as effectively web plugins for Jupyter Lab already, like a little diagramming editor for building vector diagrams. Importantly, other aspects of computing are accessible there. So the launcher will take them to a virtual Linux desktop. So if there's they need to open QGIS, they can open a desktop GIS tool in the cloud operating on the same data sets. So they're not limited to only the things that are visible in Jupyter. They can access a normal desktop environment. We run something called SyncThing, which is the Dropbox-like clone that allows them to keep synchronized files between their laptop and the cloud environment. So they can designate a folder on their laptop where if they download some data sets that they need to play with, the moment they put them there, they appear on the hub immediately synchronized. So with these tools, what happens is we kind of have the ability to have a complete compute experience in the cloud. The problem for us has become, well, a lot of people want this, and how do we grow this beyond? At Berkeley, this is for my teaching. I have engineers who can do this for me. How do we grow this beyond a few institutions? Over the last few years, this is how I got to meet Jim. Basically, Jim Colliander had done in Canada, in collaboration with National HPC Infrastructure, had deployed Jupyter for Canadian infrastructure. At Berkeley, we had been doing this with the Jupyter and Pioneer teams. The Pangeo community that some of you may know of had been doing this for the geosciences community. And all of us got together and said, we can't in our normal day jobs continue doing this for other institutions because that's not kind of within scope. So we founded a new entity called 2I2C, which is a nonprofit entity that serves a couple of needs. On the one hand, it's a service provider, right? It can sign a contract, something that I can't do with my Berkeley engineers, which is to say a set of historically Black colleges and universities would like hubs like these for their own educational purposes. I can't really say Berkeley's engineers are going to do that as a service because it's just a little bit beyond our scope. 2I2C can be the entity that mediates that. We collaborate, and they collaborate with the Berkeley team, but they can sign those kinds of contracts. But they do it in a way that guarantees that we contribute back to the open source community that feeds. So the people who work for 2A2C, the engineers who are there, are also part of the open source teams, and they contribute back. All the work they do is being put back into the open source stream in the spirit of what NASA is now requiring via TOPS and related programs, right? And importantly, 2A2C encoded something, and this goes back to those slides that I was talking about earlier about models of computing that encode the customer's right to replicate. Yes, 2A2C is a provider, and it will deploy hops for you if you sign a contract with them, but that the work that is done there will be done in a way that you can replicate it if you need to. So nothing that 2I2C does will ever rely on any piece of proprietary code that you are not allowed to take elsewhere and run on your own. And we believe this is a really important principle to hold on to when building infrastructure for science and for education. And so by having created this, we now have both examples of teaching at places like Berkeley, where we have this kind of workflow, and the Pangeo community and Jim in Canada and so on and so forth. But we also have now an entity that lets us deploy this with others and for others, and this is already happening. And so at this point, what this has become for me is effectively that I access these hubs. One of them might be on my laptop, right, where I can actually install my own software. I could be logging into NERSC, one of the nation's largest open science supercomputing centers, where they run a Jupyter Hub. We can be deploying a hub for the solar physics community, which we did a few weeks ago in Colorado, or I can be running mine at Berkeley. I have a similar one to the Berkeley one that is only for research that actually happens to run on Amazon. But for me, all of these things are simply views into my computation and my data. They have maybe different people that are here. I work with my students. Here I work with my colleagues. Here is just me. They might have different resources. At NERSC, I have access to thousands of GPUs that I have nowhere else in the world. But at the end of the day, my science kind of feels the same across, and I just move between resources as is appropriate for either the specific hardware needs, the data needs, the compute needs, or the human needs of whoever, whatever the context is. But ultimately, it is becoming a reasonably, not perfect, but reasonably smooth workflow. And I hope that we can continue with these communities building the rest. We are trying to engage with the solar physics community to try to do more of this. And at this point, if I can figure out how to stop this. Oh, I don't think I stop it here. I think I have to go back to Zoom and probably, okay, stop sharing. Here we go. All right. So, and I see that I was roughly where yes, stop broadcasting, roughly where I wanted to be, which was at about the half-hour mark, so that there would be ample time for discussion. And if there was anything on the chat, I totally missed it, because like on the iPad, I don't see anything else. So if there was anything else anywhere else, I apologize. Let me take a look at the chat. Oh, okay.
I think it was pretty quiet on the chat.
Yeah, I don't believe there was anything.
Okay, yep. Oh, I hope that was useful. I'm happy to take questions, input, or if you have other business in your call with your community, by all means, I'm here to help in any way I can.
Mm-hmm.
Any questions from the crowd?
Yeah, hey, this is Alec. Thanks, Fernando. That was great. So NASA and other folks, they have what is it called? Data management plans, right? So how do we get software management plans for folks like NASA headquarters to do, right? Because I feel there should be a delivery of software management plans, and really I'm coming from the direction of how do we make sure these folks deliver software that are, federally funded, and it makes sense to do it in all open source. So who is lobbying, for lack of a better word, folks at NASA, other NSF for that type of thing? Because data is great, but software makes it move. So just want to get your sort of reaction to that. Thanks.
Yeah, that's a really good question. And to be honest with you, what I've done in the past, at least what I personally have done, is I have interpreted the data management plan sections of NSF solicitations liberally, and I have personally included software in the data management plan. So because most of my projects tend to produce, like the kind of work that I do doesn't really, I consume data, I don't produce a lot of data. So in the projects For example, some of this work has been funded by NSF with a project called Jupiter Meets the Earth. What we put in our data management plan was actually our software management plan, if you will. Now that's not ideal, obviously, because I think I do that because I'm heavily invested in doing this well,
Right, that's up to the individual,
and so
right?
Yeah, I do it, but that might be an easier path rather than trying to open a new front on that debate. It would be to use the data management plan that exists and actually extend them to say data and software management plans, and maybe revise the guidelines to make them a little bit more comprehensive now that we have experience with both, and tell research teams that they should include both. That's how I've interpreted it. There might actually be guidance that covers some of the software stuff in the DMP language already. I to be honest with you, I haven't looked in a while, because from the beginning when DMPs became requirements, I interpreted them immediately as like, well, that's what I'm going to use. So I haven't actually looked at the specifics, but that's how I would go about it.
Understood.
I think there's usually like a small bit that says like, write a paragraph or so about how you're going to do your software, but it always is counted in the page limit. So there's some pressure to keep it short, which is unfortunate.
Sure. And I do agree with Ryan's point that what's happening with TOPS is a great place where this conversation can happen. And I think out of TOPS, those could be outcomes, actually, Alec, to your point, of improvements or revisions to how those policies are made. TOPS is a program that is thinking about the continuum between software and data as basically it's kind of two wheels of a car, the right or the left wheel, or neither of those wheels is more important. You can't go anywhere without either of them. And so at this point in science, we need both. And TOPS is a program that is looking comprehensively at these. So that may be a great place to have these conversations, because it will influence policy.
Did you see Rebecca's comment about how you'd be a good leader / champion for this?
I'm sorry.
Yeah, Rebecca just mentioned, Fernando, you would be a good choice for the TOPS leaders / champions advertisement that is out right now.
Oh, thank you. I haven't seen which advertisement it is, but I should disclose that I am on the TOPS community advisory panel for this year. So I am in one of those programs. I'm not sure which one you're referring to. I may have missed that particular the one that you're referring to, Rebecca, and I'd appreciate if you have a link. But I am on their community. What are they called? Community advisory panel is I believe the title, and I'm serving on that for the current year. And I should say I am like Shel Ganteman's biggest fan on earth. I have nothing but respect and admiration for what she and her team are doing with TOPS. I think it's really, really, really important and extraordinarily valuable.
Yeah, I like to hear this. Yeah, I guess just as one more compliment for me, I think you hit all the points of reproducibility here. I've had my head deep in this problem for the past few months, writing the paper I just sent out, and yeah, you got it. And NASA TOPS is pushing everyone in this direction. This is a good time for open science.
Wonderful. Yeah, I'm delighted to hear that you're doing this work in this fashion. You might be interested in just Google something called "Show Your Work" in one long sentence. Show your work. It's a little project by an astronomer cosmologist that I actually saw by pure coincidence. I saw him giving a talk at Berkeley this semester, and it was so on point to the topic of the class that I invited him to guest lecture in my course. It's kind of an end-to-end little, fairly opinionated but interesting pipeline to basically do reproducibility, and he's done a lot of really neat work at the LaTeX. It's a little bit tied to LaTeX, but it's very well done. With he's kind of engineered tools and icons and connections to Zenodo to basically do a fully it's that one to kind of engineer a full end-to-end reproducible workflow. He's a astronomer cosmologist in New York. Rodrigo, I'm blanking on his last name right now. I mean, it's embarrassing. Anyway, Rodrigo Luger. He gave a lovely guest lectures to my students, and he's working on a tool kind of in this spirit. And I am polishing that. I'll be teaching that course again in the spring. And my I'm not happy. I'm happy with how the course turned out and the outcomes of the students. I should have updated the slides with my current student projects. I'm not happy with the state of the course materials as they are online currently, because I think on the fly, we cleaned up a lot better the structure of the course. But my TA and I are going to be teaching it again. He's one of my PhD students. He's a physicist by training also, and we'll be teaching it again in the spring. And I think after the spring, we'll have a clean version of that course that I would be happy if people use. I mean, people are welcome to use the materials as they are right now, but they're a little bit messy. But I do think a course like that can address this at the undergraduate level, so that these practices become just the norm for students. And I've had, one thing that I should mention is I have taught this course several times at Berkeley already, and I have had students who have said after that they've asked me to be on their master's, either undergrad senior thesis advisors, master's advisor, and PhD, to be on their quals committees, because they've kind of learned to engineer the rest of their workflow in that way. So students do change their practices if they learn these things, and it's just an undergraduate course that they find fun and useful, and they learn a few useful things. We've imbued it with one of the exercises they did this term was actually replicate one of Shell's papers, one of her previous her last not fully open science Python paper that was in MATLAB. And she gave a guest lecture about her research. She gave them her MATLAB scripts, and they had to replicate her figures by working in the cloud together. And so they work with real world physical data and real research. And undergrads from all disciplines get into this, and they're perfectly capable of picking up these skills. So when we hear that doing this well is too much for scientists, I don't buy it, because I see undergrads doing this. Like, I know that my undergrads can do it like semester in, semester out.
Yeah, to that point, Fernando, like I just completed a 2-year project, and I tried my hardest to get my collaborators to use Jupyter Hub, free resource. It was damn near impossible, man. Like, wow. I could not do it for the life of me. And I don't know if they're stuck in their ways, or just uncomfortable not working in their local dev environment. But you know, I do my best while keeping up with relationships, but I don't know if you have any words of wisdom other than cracking the whip, by saying like, this is a deliverable in a contract, and really boxing them in and making sure that, you know, you don't get paid unless you do this in the dev environment, right? So I'm happy to hear that, because that's the other biggest challenge that I've run across, because we set up a wonderful environment to do all this. We IP whitelist them, and we go through all this effort, and then nothing. So appreciate any guidance.
Yeah, I mean, so I will throw out the slightly, and I'll throw it out and then I'll pull it back, the slightly hostile science advances one retirement at a time, right? Because sometimes there's an element of that, right? But I do think we can try it, and we should, and I do try to bring as many people as we can into the fold, not only the undergrads who are the next generation. I think we need to do that. We need to bring the next generation to better practices, but I also think we need to make this welcoming for the others. And there, I think a lot of it has to do with two things. First, trying to understand what are legitimately their problems and their concerns. For example, the hub, I feel that this past spring semester was the first time that I was completely comfortable doing this in the hub. And it amounted to a bunch of little things, little nags that persisted, and that in previous semesters were still not quite right. And even I, the true believer, the carrier of the torch, would not fully do it because it was still annoying. And finally, we got things like editing of dot files, cleaner access to make files, a bunch of little nagging things that kept making the workflow just annoying. We finally cracked all of them. And I finally felt like, all right, now we have something that's starting to work. It may be that for some of them, it amounts to a few of those things that just like drive them crazy, and that they're, oh, if I can't get this one thing or this one tool, then my workflow breaks. And so understanding that, making a list of those issues, trying to tackle them if we can with Jupyter, we are open to that. Like, we are open to putting resources in Jupyter into smoothing that out to the best of our ability. So that's kind of on the one end. The other side is showing them things that make them go, I want that. And I can't do that anywhere else. To give you a very concrete example, Shell's paper, right? Shell's paper was a paper about heat waves in California in 2014 through 2016, and the connection of inland heat waves with sea surface temperatures. When she published that paper, she had to download a crap load of HDF5 files, right? She says that it took her actually several months to do the download and pre-processing manually with MATLAB scripts, very cumbersome, and literally months of work, right? To download and aggregate the data so that it would be ready for actual science, right? Now, our students were given her analysis scripts to do the rest of the work. The download code was one line. And this is because Shell had, in the interim, she had made a ZAR data set that is on AWS of all of that as a single X-array readable data set in ZAR. But the line of code that reads those data is one line, and we timed it. If you run that line of code on our Berkeley hub, which is on Google, it takes 5 seconds to execute. If you run it on a hub that's on AWS, which is the same provider, it takes 1.5 seconds to execute. And that's the kind of thing that makes people go like, I want that, right? When you show someone the workflow that took you 3 months of painful teeth grinding labor with like manual file management, nobody likes that. Well, we all do it because we have to, but none of us likes that. And you turn that into one line of code that says xarray.open dataset URL, boom, 5 seconds, you have your data set, you have your little like summary HTML live view of your data. That makes people want to say, you know what, maybe I should try to learn how to use this damn thing, right? And so I think it's both, right? I don't want to go with the stick. It's more the carrot of this is desirable because it opens opportunities that for you were unthinkable in other workflows. And on the other hand, we acknowledge that this may have some issues. Let us understand what they are for you, and we can try to fix some of them. And I try to have a combination of those, but it would take some digging into what made your color. Like by digging, I mean sitting down with a person for a half hour and saying, okay, show me what the problem is and let me take notes, right? And seeing, can we crack your problem? Can we, for example, I have a collaborator who's really set into using VS Code on a glacier modeling project in Julia. Our hub has an embedded VS Code environment so that he can run on VS Code in the hub. We've worked with him. I had one of our engineers like flesh out exactly what he would need so that he would be happy in the hub. We need him to be happy in the hub. I don't need to force him to do things my way. I just want him to be in our hub because that's where we have the data, where we have the models, where we have the GPUs. So it's a little bit of both, but a lot of it is very, very much about user engagement. I don't know, I hope that helps. And I would be happy to hear the details of what made some of your colleagues reluctant, because that is informative for Jupyter. And sometimes you crack 2 or 3 users' problems and all of a sudden you've solved the problem for 1,000 people.
Yeah, it was so I agree with everything you said, right? And I think also it was a relatively small project, right? So we're talking around 50K, right, for the user, and they're like, all right, it's not maybe worth it for them to go out and get out of their workflow. I think data is the biggest carrot, and that's why I'm really looking forward to see what NASA HDRL does, because if they adhere to this sort of helio cloud stuff and they're able to have a bunch of carrots by saying, yeah, that is a lot of what you need is already there, but then also these sort of processes or step mechanisms in which follow this 10-step process. And if your data isn't there, you can basically have it there by following the same process and making it as low lift as possible. But yeah, I understand. It was one of the users was IDL. So he eventually did do one Python notebook, so it was a success. But then the other, I think it was just a lot of these co-Is too, they have postdocs and things like that. So I'm talking directly to the co-I, right? I'm not talking to the postdoc or the graduate student, right? And so that's yet another chain of communication that needs to occur, which doesn't occur, especially in these sort of low type of projects in terms of funding. But no, understood, and I completely agree. So thank you.
IDL, by the way, IDL has, or at least had, I don't know, I've never used it, but I saw a few years ago that they had a Jupyter kernel. So that could be the thing to do, is to say, you know what, we'll configure this particular hub with a kernel in case that helps someone.
And I know,
I mean,
yeah. Jack's on the phone, and I know NASA with the Helio Cloud is working to have an IDL dev environment too. So
Okay,
I
cool.
think that's sort of the best of both worlds. So yet another carrot on that side for software.
Another carrot to highlight to people is that, to me, is sometimes is amazing, is the fact that when you land on a hub, you get a little menu depending on how it was configured. It's like,
yes,
yeah, little
dashboards are
computer,
cool, man.
medium computer, big computer, really big computer.
Right.
That's a flexibility that you don't have with a laptop. It's like you can transmogrify your laptop into having a terabyte of RAM by pushing a button. You can't do that in a local environment, right? This is like open two different views with two different vastly more powerful hardware resources onto the same files. And so here's a little cheap one that costs, I don't know, 10 cents an hour so that you can do lightweight editing. All of a sudden you need to do a big run, open the big one, click one button, and your computer sprung up a terabyte of RAM, or it sprung up 2 GPUs or something like that. That magic is physically impossible on a real computer, on your desktop, right? By definition, that is one of the magics of the cloud that can be a game changer, right? If you were RAM limited to do an analysis, being able to just push a button and restart your workflow with 10 times the RAM, that's not something you're going to do on your laptop. And so things like that show access to data, access to compute, access to types of compute resources, those things can be enticers to people, for people to say, okay, I'm willing to maybe learn something new. I'm willing to try to do something differently.
Yeah, absolutely. Yeah. Thanks again.
Just a comment from a little bit ago from Rebecca. The course that you're working on, and those similar to it, would be good offered online to the general public.
Oh, Rebecca,
if there's any intention of doing that.
Yeah, thank you. Well, so yes and no. I mean, obviously, in its full form, it's not practical. It's a semester-long course that's pretty intensive. It's 2 lectures a week, 1 full 2-hour lab a week with a TA, 70 students, very hands-on, group projects, or something like that is not really valuable. But one thing that we are doing is we're trying to dissect a subset, and I'm working with that on that specific issue with my GSI, with my TA, with my PhD student, is we're trying to dissect a subset of that course that would be like the minimal backbone of that course that we could imagine teaching at an event like Jack Ketty, where Ryan invited us. What could be, and it was partly inspired by some things that we did a little bit ad hoc at the event, which is, what would you imagine having as perhaps 2 hours a day of lecture, or an hour and a half a day of lecture, in the context of, say, a week-long workshop or week-long conference, that you could teach a few of these lectures and give people at least the basic core skills of this, and a place to run it, and a kind of a to-go version of the course. If we can flesh that out, and we have a few upcoming workshops in cryosphere science, which where domain-wise where I'm spending most of my time these days, where we're going to test run all that. And if we can get it to a point where we're happy, I could much more easily imagine, for example, at least putting a little condensed website for those materials extracted out of the long course materials, and say recording a few of those lectures to put them online. So I think we may get to a version of what you're describing. I don't think it's realistic for me to do the full big one, and I don't have the bandwidth to do like a full-on MOOC version of it. On the other hand, if somebody has the bandwidth for that and has the interest, the materials are all open. And in the spirit of open science, I would be delighted to collaborate with you, Rebecca, or anyone else in making a version of that open and available to others online. It doesn't have to be, I don't have a monopoly in teaching this well, and so I would be very happy to collaborate with someone else.
Excellent. Thanks, Fernando. Let's see. Jack, you had your hand up first.
Hi, Fernando, enjoyed your talk. Thank you very much.
Thank you.
With the data that you have in the cloud, do you also build like search services on top of the data? Like, say I want some particular time range or elevation, or I want a particular subset of the data. So are those services also built? And did you build, and how are those things built?
Yeah, it's a great question, Jack. And the personal answer is a very specialized and partial yes only from me, but from others, I'll say a little bit more. So from me, as I said, most of what I do is more of data consumption than data generation. So I'm not really a specialist in exposing interfaces and UI and workflows for people to really access data well and flexibly, and things like what you're describing, requesting subsets and so on and so forth. There's a lot happening in that space right now, and that is really right now the frontier. Ryan Abernathy, who's a co-founder of the Pangeo project, coined a great acronym that kind of goes beyond the FAIR acronym. I think is an acronym that was developed, I think, in the mid 2000s maybe, and is not quite. It's not wrong, but it's insufficient. It's necessary but insufficient for today's data needs. The acronym that Ryan coined is ARCO data, analysis ready, cloud optimized data. The idea being, it's not only that I can access the data, but it's not useful to me if what I have to do to get it in the cloud is some very complicated process like the one you're describing for finding which subset I need, and then where do I download it? And if I end up effectively downloading from a cloud provider a bunch of data to have in the cloud a folder full of HDF5 or NetCDF files, and we all do that, what we're going to end up doing is just like doing a multiplication of the data in ways that are a little bit absurd. So the question is, how do we create data that can be analyzed natively in the cloud, and what are the workflows from the providers to the creators of intermediate data for that to be as smooth as possible? A lot of that hasn't been done. The technology doesn't fully exist. We're coming up with the patterns, with the APIs, with the tool chains. Some things exist, but there's a lot to be done. Now, the partial yes that I have for you is an example from a project using Maven data from in Mars. My students have been collaborating with a colleague from the Space Sciences Laboratory. And there, what we did was, and it actually has required working on the hub. This goes back to some of Alex's questions about workflow. We had to work on our hub, on our research hub, to set up a persistent database service, right? Because what we wanted to have was an actual database, an actual SQL database that had some of the intermediately processed data to do further statistical analysis, but you needed to do queries in SQL against that data set, right? It wasn't the raw Maven data that's available, but we needed to organize the raw data in an intermediate way, and the best way to do that was a database. And so Abby, this postdoc at Space Sciences Lab, Abby Azari, who led the project, together with my students, had been working. Initially, we were doing it with SQLite. It has a bunch of limitations. We're working on how do we set up a persistent Postgres server so that a team can say, here's the data entry point for this project is an actual persistent database entry point. And so we're evolving, right? We're kind of evolving, understanding the patterns. And this is where it's good to have the science co-design the technology, right? We're doing science, but we also have access to engineers with whom we're co-designing the infrastructure itself to meet these use cases. So those are kind of two different directions. Pangeo Forge is a project led by Ryan Abernathy, kind of in the NSF funded in this direction of ARCO data, of moving us to a better workflow in the cloud. But there's a lot. The point you went after is like the big future frontier. That's where the most work is going to have to be done in the next few years.
Okay, I took a note of that acronym, and I'll pass that along to my colleagues. They'll be very interested in this. Thank you.
And Ryan Abernathy, if you Google that acronym, Ryan Abernathy, you will find he has some very good blog posts and talks online. He just gave a talk at ESIP last week at the ESIP conference in Pittsburgh last week on this very topic. So there's a lot of work being done in this space.
Okay, great. Thank you.
And I think, Rebecca, you've had your hand up for a while.
Mm-hmm.
Yeah, sure. So my thought with the comment was not to offer the course similar to yours online for everybody to take at once, because I've taught before, that doesn't go well. But my thought was more to adapt it for different institutions for their own internal training. Mm-hmm. Right. So just for example, so I know NASA Goddard has a teaching division of sorts where people offer classes in Python. They offer classes on how to use these types of technologies online, but there's no real class about, okay, how do I do this the right way instead of getting lost in GitHub, right? Mm-hmm. Like so many of us beginners do. So like kind of loosely copying and pasting across different institutions and letting, and like the whole NASA Tops thing about training the trainers, like not just at conferences, but to spread this across different institutions and different, even commercial companies and those kinds of things. What do you think about that?
No, absolutely. I mean, I think these practices need to spread out. The carpentries has been the initiative. Software carpentry and data carpentry have been the initiative that has been trying to spread this kind of knowledge now for. I was actually surprised. I looked last week online because I was describing the carpentries to someone. For those of you who are not familiar, the carpentries is an initiative that was created precisely, basically, by computer scientists originally at Toronto, Greg Wilson, to sort of teach physical scientists, kind of people like ourselves in this call, how to do computing better, in a sense, right? And the carpentries was founded, I thought it was much later. He actually started it in workshops that he started organizing in 1998. It really goes way back. And yet, despite the fact that it's a big international organization that has that train the trainers model, that has, I use multiple modules from the carpentry's lessons in my course. It has directly influenced the thinking of NASA Tops and others. We're still not there. We're still not there. And I do think that one of the things that is effective, very effective, is what you were describing, sort of more local teaching within organizations, within companies. So doing that work, I don't know your community, Julie. By your, I mean sort of this community, the PyHC community. I don't know exactly how you folks operate, but within a community, that knowledge spreads much better than in more kind of generic agnostic ways, because you can imbue it with the flavor of the data that matters to people, with examples of the tools that are relevant to people, with things that are immediately useful to people. You can solve a problem that matters to them rather than saying, well, let's imagine we'll load some generic genomics data set. You may think, well, I mean, yeah, genomics is cool, but it's not what I do for a living, right? And so having things that are concretely applicable to your community is very impactful. And so to the extent that that can be done inside either a scientific community like yourselves, even if that cuts across institutions, or within an institution. I also know at Berkeley and at LBL, we had several groups that did teaching of this kind of thing in like lunches. It was Berkeley had at the Data Science Institute at Berkeley at BIDS for a while. There was, I think, like a tools lunch where people would just like come, bring your laptop, and every week somebody would say, hey, I learned these cool things about how to do this on Git, and I will teach you today. I'm going to teach a lecture today about, I don't know, web visualization with this new tool that's not Matplotlib, so you learn about it. And gradually people do pick up these things. It may be a little bit chaotic, it may be a little bit disorganized, but it has value in having that kind of organic community element and also a little bit of serendipity. So I don't think we have a single answer to this, but keeping those ideas in mind that are connected to the local community can be valuable. There needs to be a paid teacher and possibly a fee for attending the class. Yes, if it requires, yes, things like what I was describing within a community of things like lunches and whatnot, those things can be done somewhat informally. Of course, if we are expecting something that has a much longer structure, then yes, no, this cannot be done on a volunteer basis. I mean, when I teach that course, it's my job. Like, it's literally, that's the course that I was assigned to teach that semester. That isn't my job for the semester. These are students who are taking that for credit, who are enrolled. And so, yes, at scale, these things do need to be paid for and sustained. Julie, I love your cat, by the way. I have 3. I'm not at home today. I'm in Colombia right now. Otherwise, there would be 3 cats running around. But that's one for me. That has been one of the joys of Zoom, is cats on work meetings.
Indeed. Yeah, 2 kittens, and they keep trying to destroy everything.
I think Rebecca said that Will had a question.
Yeah, I was about to point to that. So regarding platforms for computing, NASA has long relied on large, more traditional HPC platforms. Should we be retrofitting these to do more scalable analysis, or just going all in on cloud platforms?
Oh, I think yes. The answer is yes, meaning both. And I tried to point to that with my last slide, that one of the hubs that I use is actually NERSC, which is an HPC platform, right? Now, NERSC, the next generation machine at NERSC, has been designed for analytics workflows. So I think
That was an
All the
abrupt
suspense
exit.
builds. I wonder if his iPad died or something. In any case, I can wait around for another minute to see. Oh, there he is. If anyone needs to drop, though, this is still being recorded, by the
whoops.
way.
Sorry about that. I've discovered that these stupid things, you can't touch them because they hang up. If you touch them the wrong way,
Wow.
they hang up. But I was going to just finish to say to the question, because I just realized we're also past the time, that HPC platforms are evolving, and NERSC is a great example of that, of an HPC facility that is evolving to be much more analytics friendly and to support not only a big supercomputing run where you submit a job with a queuing system and then you just wait for the results and it's just one big MPI job, but also to say, I want to log into this thing and access the outcome of a simulation and then do machine learning on it with 10 GPUs for 4 hours interactively, right? And so the HPC facilities are evolving in that way, number one. And number two, I think the HPC facilities can evolve, and at least NERSC, I know for a fact, is working on that, to be more cloud friendly in the sense of bridging to the cloud. Because what I can imagine is I have my environment in the HPC center where I do some of my work, and I can have the same environment in the cloud. And then depending on which data set I need to work on, I will open one or the other. And ultimately, it's my same science, and I can think of the HPC center as one resource, the cloud as another resource, and I use whichever one is more appropriate to complete the project. It's not, what I just said is not highly non-trivial, all the way from things like, well, Docker containers don't run on craze out of the box. You have to use things like Singularity and so on and so forth. There's a lot of technical weeds to get into that we won't right now. But I think the vision of both HPC facilities evolving in their the workflow they allow in-house and having better bridges into the cloud, those are both ways forward. And at least I know the team at NERSC is very friendly to that. And the team at NCAR has also been doing something like that. Oh, cool. I'm glad to hear that. Jack just pointed this out.
Yeah, thanks very much for that answer. I think I tend to definitely agree with you that it needs to be a mix between the both. I know that, yeah, both NERSC and NCAR have been kind of the most sort of progressive HPC institutions when it comes to adopting those workflows. I think the big ones for NASA are Pleiades at NASA Ames, and then also NCCS, yeah, that's what Jack put in there at Goddard as another big one for us. I think it's the challenge is kind of communicating to those more traditional HPC centers about what the differences are in our workflows versus more like traditional, like you were saying, like MPI, give me, 100 nodes for a month versus give me, 100 nodes for 10 minutes and then scale back down immediately.
And I'm happy if it helps. So, because I do know it can help, to put folks in touch with some of these teams. The team at NERSC that has done that, they're my colleagues. I work with them. I'm kind of part of the same unit. We have grants together, and we work very closely. They're the team that leads security at Jupiter, is led by the NERSC team, Roland Thomas and others at NERSC, and they actually helped NCAR in the early days. I put them in touch, and the NERSC team helped some of the NCAR folks because there's also policy issues and whatnot. It helps if you can say, look, DOE already reviewed this, DOE already did this, they have a policy in place around security and so on and so forth. And so to the extent that it could be useful for NASA and NASA Ames, you can let me know. You can contact me, and I'll be happy to make some connections in case the lessons learned at NERSC and NCAR can help other of the big national HPC facilities move forward. I'm more than happy to help make those connections if they're not already in place.
Thanks. Yeah, that would be super useful, I'm sure.
For sure.
Wonderful.
Well, Julie, I don't want to keep you any longer than necessary. This has been already fantastic, and for me, I've learned a lot. I hope it was useful for some of you. It was great meeting some of you that I've heard about. So I don't know if anybody has other questions. Otherwise, I want to let people go on with their day. I don't want to hoard anyone's time.
No, thank you so much, Fernando. Excellent discussion, excellent presentation, and I'm glad that you were able to make it today to talk. Let's see, does anyone have any final question they want to ask before we wrap up? Okay, Cool. Well, thanks again, Fernando. And I'll personally see you again soon. But yeah.
Wonderful. Well, thanks everyone. Take care. Goodbye. Thanks for having me.
Yeah, it's been great.
Of course. Thank you for coming.